Good day everyone. Today I will be presenting a key insights from an important study titled Characterization of Permeability and Combustion of an Iron Ore Bed conducted by organization. This research highlights how permeability both before and after ignition affect sinter bed behavior and ultimately a sintering plant productivity. Now, coming to our next slide, which is about the permeability in sintering. In sintering, a consistent and efficient airflow through the iron ore bed is essential for productivity. This airflow depends on permeability, which we classify as cold before ignition and hot after ignition. Cold permeability is influenced by green mix structure, especially moisture and granule quality. Hot permeability, however, is determined by the resistance posed by the flame front. Both are critical to understanding how sintering reactions progress and how to improve strand performance. The pilot plant experiments used three types of ores and other typical sintering inputs. A specially designed center box were used with thermocouples and pressure sensors embedded at various levels. Importantly, a ring of fine sand was placed around the bed to prevent air leakages at the sides, ensuring accurate measurement of gas flow through the center mix. This setup allowed close simulation of actual center plant condition. After ignition, the gas flow rate drops sharply as the flame front forms due to increased resistance. As the sintering progresses and the flame front moves downward, both gas flow and flue gas temperature rise again until the burn through point is reached. Thermocouples and pressure sensors clearly track the flame front by identifying the point where temperature peaks and pressure drop simultaneously, signifying passage of combustion zone. Several operating parameters influence permeability. Firstly, moisture content must be optimized. Too little or too much reduces permeability. The sweet spot for maximum permeability is around 6.1 to 6.4%. Second, suction pressure. Increasing suction enhances gas flow and reduces flame front resistance. Finally, coke breeze content surprisingly showed only marginal influence on flame front resistance within the tested range. To validate the pilot finding, plant trials were conducted at the plant. Gas velocity was measured online using pilot tubes placed below the sinter bed. The results confirm that the post-ignition gas flow or hot permeability correlate better than productivity than pre-ignition measurements. Monitoring the flame front online also allow us to dynamically adjust suction pressure and strand speed, improving control and output. This slide shows temperature profiles from both the north and south sides of the center bed. Differences in ignition or bed loading can cause asymmetry in flame front development. A wider flame front seen on north side implies slower progression. The south side had a narrower and faster moving front. This variation directly influences the hot permeability and gives us another lever to fine tune strand operations. In conclusion, Both cold and hot permeability are important, but hot permeability offers a better real-time control variable. By monitoring flame front resistance using temperature and pressure profiles, we can fine-tune suction, moisture, and strand speed. These enable a more stable process, improved center quality, and higher productivity. The developed method provides a solid foundation for optimizing center plant operation.